Given a heat engine represented by a rectangular cycle with pressures P2 larger than P1 and volumes V2 larger than V1, what is the net amount of work done in one cycle? So I'm going to sketch what is there on the slide onto the board here so that I can look at this in some more detail. So we have this kind of maybe square, maybe rectangular shaped. It's hard to tell. It doesn't really matter actually whether it's a square or a rectangle. Maybe rectangle would be the better thing to say because a square implies symmetry that's not actually there. And based on the description, I think it would be fair to say that since P2 is larger, that's where P2 is going to be. That's where P1 is going to be. And since V2 is also larger than V1, I'm going to say V1 is right there and V2 is right there. And of course, we're talking about motion in a clockwise direction. So there's the motion we're going to look at. And if I look at the work output that represents this section right here, right? So this, if I label kind of maybe 1, 2, this would be the work from 1 going to 2, and then maybe, maybe I can say 3, 4. If I thought there was work for 2 to 3, I'd call that work sub 2, 3. But since that doesn't involve a volume change at all, I think the work for these vertical parts of the cycle are going to be 0. So the other work I might be interested in calculating is the work going from 3 to 4, where we actually see a volume change. And so for the work going from 1 to 2, the formula I'd like to use for the top part and the bottom part, those are isobaric processes. They're happening at constant pressure. And the formula for an isobaric process for the work was pressure times change in volume. So for that top part, that's going to be P2 multiplied by the volume change, which would be the volume at 2 minus the volume at 1. And we can see that if V2 is larger than V1 and P2 is naturally positive, this is going to be a positive amount of work done by the engine for what maybe corresponds to the power stroke of this engine, even though this is kind of a strange shape for a real engine. In turn, the work from 3 to 4 would correspond to the pressure P1 multiplied by V4. Actually, wait, should we say V4? I said V4 because I was looking at this 4 right here, but that really corresponds to V1. So let me nix that there and call that V1. Because it's final minus initial, right? This is final, there's initial. So this one would be the opposite, V1 minus V2. That's clearly going to be negative. If I want to see what the net amount of work is, I have to add these two things up. And so maybe the way I could look at that is, if I add them up, it would be P2 times V2 minus V1 plus P1 times V1 minus V2. But maybe I can rearrange things a little bit, because wouldn't it be neat if I had a common factor here? So let me change what I have there a little bit here. So I'm going to change what I have in here. Okay. And if we make this a V2 minus V1, that's the opposite of what I have here. That's okay as long as I make this a minus sign, because I said I was adding these. So that's a little algebra trick I can do there. And that means I've really got P2 minus P1 multiplied by V2 minus V1 when I simplify that. And that could be interpreted as maybe delta P times delta V, but delta P is really like the height of this rectangle, and delta V is like the width of this rectangle. So what's kind of interesting about this is that that shows that the work in this case is equal to the area in the graph of the cycle in PV space. And it turns out that is actually going to hold for all engines that are graphed in PV spaces. If you can find the area within that curve, that will actually tell you what the net work output is. And so there that is expressed in the answer.